Our next speaker is Baptiste, who's going to talk to us a little bit about using radio Jove data in the virtual observatory.
Yeah, thank you. I will first try, well, there was a lot of talks about science with radio emissions. I will try to say a few more things about how those radio emissions and what's the context of those radio emissions first before talking about sharing data. So, as you all know, the sun is blowing what we call the solar wind, which is a flow of electrons and protons, which is flowing in the heliosphere, and it's hitting the planets. And when those planets have a magnetic field, this magnetic field creates a cavity, a magnetic cavity, which is protecting the planet from the particle coming from the sun. And this is called a magnetosphere. So it was already been presented. And when the sun has some eruption, which happens often, at that time usually the whole atmosphere of the sun, which is blown out at once, it hits planets with a magnetic field. And contrary to the general idea that it's at the poles that the particles are just falling down on the planet, what really happens is that the magnetic field, which is an object which is in equilibrium with the solar wind, it's compressed. And while it's compressed, in the tail, so on the night side of the magnetosphere, there are field lines that are going to touch together. And this is something that magnetic field doesn't like. And so what happens then is that it's make a null point at some point, so there is no light, it's just an illustration. And once there is this reconnection, this magnetic field line that was long, going there and back, is now a short one. And this magnetic field is like if you have a rubber band and you just release it, and it's going to the Earth very quickly. And while it's doing that, it's taking all the electrons that are around and accelerate them while it's going back to the Earth. And at this point, this is where those electrons are falling back and making the aurora. So it's not a direct mechanism, it's linked to do the solar events, but it's not direct. And then this is the regular aurora with here the radiation belts of the Van Allen belts of the Earth. Okay, the radio emissions that you are looking at, when they are linked to the sun planet, here it's a general planet, it's the Earth, but it's a general planet. When it's linked to that interaction, this is what happens. So a planet that has a magnetic field has a magnetosphere. With the solar wind, there's a hollow cavity with a shock in front, because it is a supersonic flow, and it's deflecting the solar wind. And when there is an eruption, what happens? So you have what we call a coronal mass ejection. This is the name, the matter of the solar corona, which is ejected. You have a shock also there, and you have electron beams. And those are producing the type 3 and type 2 bursts that the guys who are working in the low frequency range know. It's those emissions, those are straight emitting things. These are caused by electrons accelerated in front of the interplanetary shocks. And those wide things here are caused by electron beams traveling at speeds of a fraction of the speed of light. Then, at the planet, as I said, when there is reconnection, you have this acceleration, and then it makes auroral in the atmosphere of the planet, auroral lights, and radio emissions. So this is an example of Saturn radio emissions that are linked to this phenomenon. This is an example to illustrate the fact that those emissions are non-thermal. So these are spectra. So this is a frequency or wavelength and intensity. All spectra for all planets. So green is Saturn, red is Earth, white, black is Jupiter, and blue is Uranus and Neptune. So those are the intensities of radiation depending on frequency, and all to be compared. All the radio emission have been normalized to a distance of 1 sun of distance. And so what you see, so here this dashed line is 10 megahertz This is the Earth atmospheric cutoff. Below that line, you can't observe from ground. So actually, all the planets are emitting radio emissions, but it's only Jupiter that is going beyond that line. And here, this is the thermal black body of Jupiter. So you see, if you go down at low frequency, it's linear in this log-log scale. And so it's, well, a lot of orders of magnitudes above that thermal background. That's what Jim was saying, where when he was saying that those emissions were at very, very, very high energy. Actually, when you compare that to nuclear energy, it's because you are thinking of that energy in terms of thermal energy. And it's not thermal energy. It's resonance, so it's a little bit more complex. So there is no nuclear explosion there. So when you are there, what you will observe, and the Juno spacecraft that was mentioned by Jim, will go there, and well, the electric field in the sources will be of the order of 5 to 10 volt per meter. So it's big for radio emission, but it's not so big in Earth standards or the engineering standards. This is a plot which is similar to one that was showed by Chuck. So you have those magnetic field lines. This hollow cone of emission has already been introduced. Here I put an electron which is spiraling around magnetic field, and just to try to explain you why there is this cyclotron emission at the frequency of this spiraling rate. Is just, if you imagine an electron which is turning around, it's the same as if you have an helicoidal antenna. Then the mechanism of emission, which is a little bit more complex, makes that there is energy which is emitted only in one direction. But this is why it's the cyclotron frequency. This frequency is the rate of rotation. And I like this picture. If you could see the limits of the magnetosphere of Jupiter, this is how it would look like. It would be the largest object that you would see in the sky. It's a huge object. But you can see it. Jupiter is just a little point here. Example of spectrograms. This is a Jovian Voyager 2 observation of Jupiter. I just randomly picked a spectrogram from the Nancy Observatory in France. So these are S-bursts. So you see, this is 3 seconds of data, around between 22 and 13 megahertz. And if you zoom into that, this is Kharkov data in UTR2 data in Ukraine, and this is 115 milliseconds. And so you see those drifting tones, and I will discuss that a little bit later. Actually, now. I will try to interpret that plot. So, as it was said, so here frequency is increasing because of the fact that it is emitted at the cyclotron frequency, so which has some formula. It means that the altitude is increasing when you go down. So, and this is time. So if this is the trace of an electron, a bunch of electron emitted radio waves, they are going up in altitude while time is increasing. So those are electrons that are going out from Jupiter. If you look at the slope, you can compute the electron speed. So the slope is 20 megahertz per second, minus 20 megahertz, and it goes to the speed of a few tens of thousand kilometers per second. It's huge. And then sometimes you can see here there's a slope, there's another one, and there's a change of slope in the middle here. And so if you look at the change of slope, it means that at this point the speed of the electrons changed. They were accelerated or decelerated. So the idea is, and what could accelerate or decelerate electrons? Clearly it's an electric field. It's the easiest way to do it. And you see that there is a drift. If you look at the previous one here, there's a drift. And so in time, the frequency at which this angle is happening is not the same. So it means there's a drift also of this location where the electrons are accelerated or decelerated. From the data, if you work out the data, I will not show the details. If you look at this slope here, this corresponds to a slope of a few 10 kilometers per second in the medium there. But if you think about it, if you have a plasma, this is a classical plasma with protons and electrons. It's I think you can count, there are the same number of charges of each color, so it's a neutral plasma. And if you put there a sound wave is a pressure wave. So the electrons and the ions will react to this pressure wave and organize. So here I put a horizontal wave. But the lines are much more heavy, so they will not move, well, much less than the electrons. And so if you look at the repartition of charges, you have slices of red, which is positive, blue, which is negative, etc. And this is creating an electric field. So clearly, we can easily think that those layers are, and which are moving at the speed of sound, are clearly electric field layers that are accelerating. So this is the type of physics that you can do with those emissions. So you are around, you observe Jupiter with a high accuracy and high resolution radio receiver, and you do science at Jupiter, remotely. Okay, so when we share the data, your data, to the science community, the occurrence can be statistically predicted, so that was already shown with this diagram with IO and CML, but they are intrinsically sporadic, so there is a probability, but you don't know exactly if you will be able to see it. So we want to enlarge the temporal coverage of the Jovian radio emission, and I think that, and it was already shown, we want to observe also the temporal variability of the emission, and then for that we need a lot of observers at various places in the world. And so I think that would be a great interest to do that. So I took here two plots from May 21st this year. So one, the top plot is from Dave, and the bottom one is from Tom Ashcraft. Florida, New Mexico. If you do the math, just for fun, so this is about a little less than 3,000 kilometers between the two places. The Jupiter Earth distance at that time was that distance in kilometer and astronomical units, which is the Sun Earth distance. The rotational rate of Jupiter is so that number, a period of a little bit less than 10 hours. And the angle, as seen from Jupiter between the two observers, is 6 arc seconds. And then, so you have the speed, you have the angle, you get the time for which an event is going from one observer to the other. So it's on the order of 18 milliseconds. If you look at the speed, the trace of that event, it's half of the speed of light. So it's not information, there is no link between the two. It's just the trace, like a beacon, which is rotating. But that gives you the idea of magnitude of the accuracy that you need. And then, if you look at the data and just overlay with the same frequency, range, and time, well, it's still in the same event at the same time. So, looking at the variation in intensity, then the relative variation in intensity is interesting for science. Okay, how do we share efficiently data so that scientists can use it? So we have to provide calibrated data, but I think that was discussed is something that is already there. One thing is to provide data in a standard format. Scientists are people that have a lot of imagination, so they can cope with many strange formats. But if you propose data in a format that they already use, they don't have to write readers or things like that. They just use their software and it's finished. It's much easier. So that's part of the discussion that we have with the Radio team. And in that data, there should be metadata, which is the data about the data, like the location of observer, an accurate time for observations, the observation target name, the Jupiter or the Sun, with a set of standard keywords. This is also an important point. If you have metadata and just put the Sun in English, or if I'm French, I say soleil, or if I don't know whatever language, the computer will not know that word. So you have to use the same language and the same dictionary. And making available all this data on a networked set of databases, this is what we call the virtual observatory. So it exists already. It's a set of databases that speak the same language, and so you can ask questions and get answers, which are usually data. And It exists, it has been existing for 10 years in the astronomical domain. So they are sharing images, spectra, catalogs. There are large repositories of journals that are available. There are search interfaces, you put keywords, location on the sky, frequency range or wavelength range. And there are available plotting tools. And all this is freely available on the web. So you can either get the tools to plot, you can go to the websites and get data. And so I just put two links here, which is the US portal to the Astronomical Bureau and the French one. So in the presentation you can go and have a look. The US one has quite neat introduction on what it is. Then about low frequency radio. At the moment, there are not so much things. NASA has an archive which is called CDA Web, which is providing free access to a lot of space physics mission, so measurement in space of plasma and radio and magnetic field. There is the Virtual Wave Observatory, also at Goddard, NASA, which is providing access to radio instruments, mostly in space. So this is more specialized on radio. And here I put another link, which is made by a team in Toulouse in France, which is allowing to plot a lot of data from space missions and ground-based observations. There are not so many data sets on radio, but it's very interesting if you want to just to have a look on what kind of data you have. So just to show you why we would need this standardization of language between tools and user. What it is now for most of the scientists, so you are there, you try to find out what are the databases where there could be data of interest, you query them all, you have to know the URL, the form URL, you have to conform to the parameters that they are proposing. You get some data in many different formats, but in order to know what's there, you have to load them on your computer, write in your preferred software, language software to read each of the data sets, and sometimes you can, well, if you do it well, you can plot data, and at this point you can just realize it's not what you were looking for. So it's not, it's a process that there is a lot of time lost in the process. So the first step is to have standard formats. In this case, you just download, run your reader, or readers that are already existing and provided for those formats, and that's easy. It's already a first step, and you can use standard tools that already exist. But then you still have to download the data and go to each databases. And the virtual observatory is, you are the user, you go to a web portal usually, and you type in parameters in a form. For instance, I want on the 21st of May 2014 data from Jupiter in the spectrum form from between 22 and 24 megahertz, like this. And it's querying all the system to check all databases, knows how to answer to that question. And so they are all providing answers, and the portal is giving you a list of results with some hints. You have quick looks, things like that, so you can just look at the data before you download them. And then if you are happy with one of the data, you just click on the link, and it's going to go to the databases and download the data. And so it's really an enhanced experience that we are proposing. And the idea is to add Radio Jove there, so that it's easy to access. So now on the virtual observatory, what data are available in terms of low frequency radio? So there is the North-South decameter array, routine observations. So there are raw files at the Observatory of North website, and Dave told me that so he knew how to read these files, almost. Then the pointing files are, there's no documentation, so how you do that? There is also partial, because it's still in development, set of the data which is available on the virtual observatory on one portal that we are developing in Paris. So there's also the Iitate Observatory in Japan, and they are providing FITS files with quick looks, and it's available on the UGONet network, which is also a virtual observatory, but which is probably closer to the space physics one from Goddard than from the astronomical one. And the Vespa one is correlated to, is more into the astronomy. So there is the current Radio Jove archive, mostly quick looks and a few web files, but it's not enough to do science with that. And soon, Chuck, the University of Florida data will be available next year, probably. A few screenshots. So this is the Jovian data at Nancy. So you have here summary plots where you can select the data you want. Here you have some Jovian events. So this is the virtual observatory access that we have in Paris. So VESPA stands for Virtual European Solar and Planetary Access. So I just queried Jupiter, and I have got a list of files. And when I pass my mouse above the lines, there's a quick look requiring here. So for that line, there's this quick look. This is a file I want to download. And as this file is 150 megabytes, I'd better see the quick look before I see that there's nothing in it. This is an example of the E-Plate Jupiter data. So this is the web page where you can download the data, and this is an example of file. So you have it's a listing of files and of quick looks, and then you can plot the quick looks. So, and this is the web access. It's not the Ubernet access that I don't show here. This is the Radio Jove archive. And so you have here I selected one date, and so you have a series of files that are available. Here it's an image and a SkyPipe, I think, product. So what I'm proposing for the future of the Radio Jove software, we discussed that yesterday with Jim Sky. There is a tool in Model that we have developed that is allowing to simulate the shape of the radio arcs that you will observe at a given time, at a given place. Because it's really, as you saw, it's the radio emission is a holocone which is rotating around Jupiter, and those holocones are centered around magnetic field lines that are not just dipolar field lines that are waving around while the planet is turning. So it's really it's not an easy geometrical thing to do. And so it was done. And so there is an access. It's still a prototype, but there is no cookbook, there's no user manual, so it's not usable yet. But you can see that those are observations, and those are simulations, so it's matching pretty well. This is another tool that is proposing the same data, where you have a database of pre-computed spectrograms for a series of observatories, so E-Plate, Nancy, spacecraft like Cassini, Galileo, Voyager, even the JUICE spacecraft, the planned orbits, is there. And this is an example of, I think, a Ganymede, no, Europa flyby of JUICE, where you can see the northern radio source, but the southern radio source, no, sorry, the southern radio source arc is there, and the northern arc is there, except here, because Europa is going to hide at some point the radio source. So here, if you look with a very high resolution instrument just at the limit there, you may have information on how the waves are refracted from Europa, and it gives you information on the ionosphere of Europa, remote observation. So there are plenty of things to do there too. Just to compare, there are other projects that where amateurs are helping science. Those are led by ESA, and so there is a Venus active archive where amateurs are posting images of Venus, and the same for Meteor Observatory with the meteor shower observations. Okay, about the metadata, I will go quickly because it was already been shown in previous talks. So this is the set of things that we want to have there. In terms of formats, I will also be quick, but the CDF file is sometimes, I think, would be the best choice, but we have to discuss that. This is a format that is built by NASA Goddard and maintained and very well documented. Well, I will skip that. You will read the presentation of the key. The next steps, next 6 months, I have a project in Paris where we will set up a test server for data upload, data validation, data distribution. We will need volunteers at the end of this year to upload data. We don't know yet really exactly what we put there. We probably propose spectrograms and signal frequency, and I will be discussing with Jim to try to include CDF output directly in Skype. And then further plans, if everything goes well, I will present those developments at the next Magnetosphere of Outer Planets in Atlanta next June. And I will open the service as soon as it's there. Okay, pictures, I'm finished. So this is Meudon Observatory, large dome under the snow, and this is the solar observatory in Meudon. And this is the Research of Paris, this one, and this is the Arago, how do you say that? This type of instrument, refractor. Yeah, and it's from the 19th century. I'm finished, thank you.